Welcome. This presentation demonstrates computer-assisted retrosynthesis using Spy AI, a free resource that can be used by advanced organic chemistry learners for self-directed learning. Retrosynthesis and consequently planning for the total synthesis of target molecules can be used to measure how well the learner is able to apply their knowledge and understanding of organic chemistry principles. Of course, these two are entirely different competencies that also require sufficient practice and guidance, all of which Spy AI is able to provide using its retroscore function. This sorts predicted routes based on synthesizability according to the following factors. Ideally, routes with scores of zero point 0.6 up to 1 should be used, but for larger and more complex molecules, the algorithm often returns routes with scores of zero point 0.4 and lower. We can use the SMILES notation of our target compound or simply use the built-in drawing tool for our input. The algorithm then returns a maximum of 300 routes that are further clustered based on the series of bond disconnections and the starting materials used. A synthesis tree is shown for each corresponding route, which also divulges information on which starting materials are commercially available. If we click on the References button, it will show up to 50 alternatives or reactions sorted based on structural similarity to the reactants shown in the synthesis tree. Since all relevant information are presented, learners can prioritize reaction conditions with highest yield for the modification step in the methodology. Shown here is a general scheme for the high-scoring routes for our target compound. A retroscore of zero point 0.7 is given to routes that uses a halogen for its Q at carbon 4 because this improves selectivity of substitution reactions at this position. Learners can then similarly try to rationalize why the remaining routes have lower scores. This is an example of the original reactions that were modified to fit our target compound. It is then up to the learners to use reaction mechanisms and reagent analysis to determine whether these modifications are feasible and applicable to yield our target. After all these, it should be possible for learners to predict possible changes to the reported yield and provide corresponding solutions if applicable. After all that, I present to you our completed synthesis strategy with a total yield of 79.5%. Learners get to analyze how reagents and catalysts function in the reaction as they examine the resulting chemo, regio, and stereoselectivity caused by the modifications. By using Spaya, learners should also be able to recall familiar organic reactions with more ease and be more acquainted to unfamiliar reactions as they try to specify which reaction conditions have consistently high yields that can be used for optimization. Overall, Spaya AI provides a more realistic and practical perspective on the problem-solving processes of organic chemistry. The only limitation is that learners should use an external reference for protecting groups since Spaya's algorithm does not account for protection and deprotection steps. This may be done to maximize yield by lowering the step count as much as possible. Here are the references used in the presentation. Thank you for listening.